Hello everyone, welcome to another kinetic tutoring episode, and today we're going to be talking about the inertia of a dumbbell. So let's get into the problem. A dumbbell-shaped object is composed by two equal masses m connected by a rod of negligible mass and length r. If I is the moment of inertia of this object with respect to an axis passing through the center of the rod and perpendicular to it, and I2 is the moment of inertia with respect to an axis passing through one of the masses, it follows that option A, inertia 1 is equal to inertia 2, option B, inertia 1 is greater than inertia 2, and option C, inertia 2 is greater than inertia 1. So let's draw a diagram of both systems to see what both would look like. Alright, so here we have system that has inertia 1, mass m here, rod that has no mass, and another mass here, and the rod has a radius r. So this radius right here is going to be r, and it's going to be rotating around its center. So this is the axis of rotation. And now let's draw the second one. We have m, massless rod of radius r, another m, and this time the center of rotation is going to be here through one of the masses, and from here we're going to calculate the inertias of both of the systems. So let's start with inertia 1. So the way that we find the inertia of a point mass is it's just mr squared, where r is the displacement from the center of rotation. So here we have two m's that are both half r away. So we'll have m 1/2 r squared. This is the inertia of one of the balls, but since we have two, we're going to multiply this by 2. 2m, let's distribute this square. 1/2 squared is 1/4, and r to the power of 2 is just r squared. Now let's multiply this out, and we get 1/4 times 2 is 1/2. 1/2 mr squared. That will be r I1. Now let's find I2. So the displacement of this one from the center of rotation is going to be 0. So when we do our mr squared, it'll be m times 0 squared, which is m times 0. So this ball here is not contributing to the inertia, and therefore all of the inertia is coming from this ball here. So we have m times that displacement squared, and the displacement here is just r. So we'll have m times r squared, mr squared, which is our I2. And now, looking at both of the inertias, we notice that I2 is obviously greater than I1, and therefore solution C would be the correct answer. Now, would our answer change if the rod had a mass? Let's take a look. Alright, so let's set up the same systems again, except this time, let's say that our rod also has a mass m, and it still has the radius r, and I1 is still rotating around the center. And let's get another one going. Mass m, radius r. The rod's also going to have a mass m, and the inertia is going through one of the masses. Alright, so we know that for I1, the inertia of a rod around its center, a thin rod, is simply 1/12 mr squared, where the r is just the length of the rod. So we'll do 1/12 mr squared plus the inertia we had last time of the two balls, which is 1/2 mr squared, which will give us, this becomes 6/12, so 6/12 plus 1/12 is 7/12 mr squared, which will be our I1. And now let's check out the inertia of this system right here. The inertia of the ball was mr squared, and then we know that the inertia of a rod from one of its edges is 1/3 mr squared. So we add that in as well, and that gives us 4/3 mr squared. And as you can see, our I2 is still going to be greater than our I1 in this scenario. And from here you can tell that as a general solution, the further something is from the center of rotation, the greater its inertia is going to be. And obviously, since the r is squared and the m isn't, the displacement is going to have a large factor to play in the inertia of an object. Thank you for watching, and tune in later for more physics tutorials.